My name is Alexey. I'm a PhD student at University of Toronto, and I will be presenting our paper about JITServer, which is a project collaboration between our university and IBM. So to give some background, I'll talk about what just-in-time compilation is. Managed language runtime, such as the Java virtual machine, when you build your application source code at application build time, it is converted into portable Java bytecodes. They're platform independent, and at runtime, these bytecodes are executed in the interpreter, which is relatively slow, and this interpreter collects profiling information. And then the compilation into native code happens dynamically in the background. And it's called just-in-time or JIT compilation. And only hot code paths are compiled, and the compiler relies on profiling data to make optimization decisions. And as a result, the code eventually, the native code eventually executes directly on the CPU and reaches peak performance. So JIT compilation, while it improves application performance, it comes with significant overheads. So the CPU time spent by the compiler can account to up to half of total CPU time during the warm-up phase of the application. And the application basically has to compete with the JIT for CPU resources. And the memory footprint of data structures used by the compiler can take up to hundreds of megabytes. So if you're running something small in a small container, then again, it could be up to half of your overall memory usage. And those memory spikes are transient, they're hard to predict. It's hard to predict how much memory exactly the compiler would use. So as a result, when you want to run this in the cloud in resource-constrained containers, you have to over-provision resources. You need more CPU to maintain quality of service during warm-up, and you need this extra memory to accommodate the spikes, which goes unused after the warm-up phase. And this leads to lower than optimal application density in the cloud. So the approach that we're exploring in our work is called JIT compiler disaggregation. We decouple the JIT from the rest of the JVM and move it to a separate remote process. So it is an example of software disaggregation, and it's similar to, let's say, microservices, as opposed to hardware disaggregation, like memory disaggregation, which seems to be one of the main topics of the workshop today. So when applied to cloud computing, JIT disaggregation reduces overall memory usage because these spikes from multiple client JVMs served by the same server there are unlikely to align at the server. So the peak memory usage is lower, and as a result, you can provision less memory overall. And the JIT also doesn't steal CPU cycles from the application, which results in faster warm-up and better quality of service in small containers. It also enables independent scaling and sizing of compilation resources, which simplifies provisioning. So as we show in this diagram, in the regular setting, you have multiple JVMs. Each of them has its own JIT compiler. And when we disaggregate this, we end up with a bunch of client JVMs that delegate JIT compilation to a JITServer. So remote JIT on its own has significant drawbacks because the overhead of the JIT compilation doesn't go away, it's just moved around. And that comes at the expense of additional overhead because of communication. There is serialization, there is the networking stack, and it results in higher overall resource usage. And as we show in our evaluation, especially affects shorter running workloads. Because each compilation takes more CPU time because of the networking overheads, and it also takes more wall clock time because of the networking latency. As represented in this diagram, so because each compilation is not just a single request-reply operation, it's hard to predict what data the compiler will need in advance before the compilation. So the compiler needs to request some of the data on demand from JVM. So as a result, it takes more CPU time and wall clock time. So our approach to solve this and to improve performance of remote JIT is to enable sharing and reusing compiled code across multiple JVMs. And the main example of that is multiple instances of the same application that are used for horizontal autoscaling in cloud computing. And the main goal is to reduce overall CPU usage by amortizing the cost over multiple JVMs. So as represented in the diagram, we start with multiple JVMs using the same JITServer, but then we add caching, and a lot of the compilation requests will result in a cache hit that can be served very quickly. So while this is a very simple idea, the actually implementing it is challenging, because if you take JIT compiled code and plug it in as is in different JVM, it will most likely crash, because compiled code, it has direct pointers to various runtime entities in the JVM process, such as class metadata and calls to other JIT compiled methods. And the virtual addresses of these entities, they are not deterministic. They vary from run to run because of the differences in the order of class loads, order of just-in-time compilations, and other factors. So it's essentially random. And the compiler also makes assumptions about class hierarchies. For example, class C currently at the time of the compilation has a single known subclass. That's why we can devirtualize all the calls that has it as a target. And this assumption can break even in the same application later on because of dynamic class loading. So our solution to the fact that the code would break if you plug it into a different JVM is to store it at the server in a serialized format. So we attach to the code some serialization records to describe how to fix the code so that it becomes correct in different JVM. So we use relocation records to update those hard-coded virtual addresses in compiled code. And it's a more difficult task than, let's say, for C or any other like native statically compiled language, because we cannot simply identify all these entities by a globally unique symbol name. It's more complicated, and we'll explain in more detail why. And we also store validation records that we use to verify compiler assumptions. And the main building block of these records is identifying classes equivalent to runtime across JVMs from the point of view of the JIT compiler. So we can express all the relocations and validations in terms of Java classes. So it is important that this is a class at runtime, because the same Java class definition can result in different classes at runtime due to reasons such as different class loaders, bytecode redefinition at runtime, etc. So we assign a globally unique ID to each runtime class. So in our target JVM that we use for implementing this, which is Eclipse OpenJ9, this entity is called run class. So it's basically immutable class metadata, which includes the bytecodes of all the methods. And we associate enough information with these IDs to look up and verify the class in any JVM running on any machine. So it consists of the fully-fied class name and secure hashes of immutable class metadata of ROM classes across the inheritance chain of the class. And we do that to accommodate cases when some of the superclasses of the class for which we compile the method are redefined at runtime. And we also need to identify class loaders, because to look up a runtime class or RAM class in a live JVM instance, you need a class loader instance. And we identify class loaders by the name of the first loaded class. It's a heuristic that works very well in practice. We haven't seen any class loader misidentifications in any of the applications that we ran, but even if it does happen, it can only affect performance, but never correctness. So to give a concrete, quick example, imagine you have some code with some abstract based class, an implementation of this class, and some method in a different class that calls method M1 through type class A, but let's say in profiling, we determined that the actual target of this virtual call is normally class B. So we can inline this call as B.M1. So it's called guarded devirtualization with inlining. It's one of the most important optimizations in the JVM. So the compiled code, which I show here in pseudo x86 assembly, it starts with the guard that checks that the runtime class of the actual argument that is passed is B. And if it is, then we continue executing the inlined body of the B's version of the method. Otherwise, we jump to the slow path that performs the virtual call. And serializing and relocating this piece of code is done as follows. So The validation here is checking that class B is the same across the JVMs, and relocation is updating the pointer to class B metadata in the CMP instruction. So I don't have much time, so I'm not going to go into details of this example, but that's basically the idea. So it's worth noting that we're not caching everything, because this relocatable code where we can actually easily patch these pointers, it restricts the scope of optimizations, and it can be up to 10% slower as a result. So if we cache everything, we will hurt peak throughput for long-running applications. So instead, particularly hot methods are recompiled with more optimizations, and the result of that is not cached. And the cache hit rate is 70 to 95% in practice, depending on the application. So we improve start performance of the JVM, reduce CPU usage without hurting peak throughput. So we've evaluated our system on 3 web applications, Acmeer, DayTrader, and Spring Pet Clinic, and we present some results for Acmeer. The other two look pretty similar, and the rest of the results are in the paper, which, by the way, was published in Usenix ATC earlier this year. So we run this on a cluster of Fly machines with 16 CPU cores each, 10 gigabit commodity Ethernet. We run applications in Docker containers with a small amount of resources, and they run the JITServer on a separate machine, so there is always remote network communication in the way. So we measure start time, which we define the time from the starting of the JVM process until the application becomes ready to start serving HTTP requests. So all these, this benchmark, it's a web application. And we vary container size between extra small, which is half CPU, half gig of memory, up to large, which is 4 CPU, 4 gigs of memory. And we see that, so the blue line represents local JIT, orange line represents remote JIT without any caching, and the green line is remote JIT with caching most of the compiled code. So we see that caching results in significantly larger reduction in start time, but this effect becomes smaller as we increase the container size, because there is more spare CPU for the JIT to do its work during the start. So overall, it's up to 58 reduction in start time. That's the maximum across different applications, but about half on average. So we also measure warm-up time, which we define as a time from applying the load until reaching 90% of peak maximum throughput. And we configure the workload to saturate the application throughput so that the peak throughput is actually the absolute maximum that the JVM can handle. And here we can see that even without caching, we decrease warm-up time by up to 80%. And this is mostly due to the parallelism, because the server is likely to have more additional CPU resources. And in this case, caching doesn't improve additionally as much, because warm-up is when those recompilations at higher optimization levels happen, which we do not cache. So those were for a single application instance. And now the next set of experiments, we measure overall CPU usage, which is the main target of caching. So we're on up to 64 JVM instances concurrently that are started with a short interval of a few seconds, and they run for a fixed duration between 2 minutes and 10 minutes, and over a period of time of 1 hour. So we're kind of like simulating cloud deployment, where things are deployed and started on demand and shut down. And the CPU cost is the total amount of CPU time by all the JVMs and the JITServer per amount of useful work done, which is requests served by the web application. So we see that for short-run application instances, 2 minutes in this case, remote JIT on itself without caching actually increases overall CPU usage because of those serialization overheads, networking overheads. But at the same time, with caching, we reduce overall CPU usage significantly up to 77%. Again, the effect becomes smaller with longer running application instances because the CPU overhead of JIT becomes relatively small compared to the overall CPU time used by the application. And We also measure the reduction in overall memory usage. And you can see that remote JIT itself without caching achieves most of the benefits, and the benefits are up to about 60% reduction. Again, it's because those spikes in memory usage from multiple clients don't align. So those spikes, they're mostly attributed to, again, those recompilations at the highest optimization levels, and those we do not cache. That's why caching doesn't have much of an effect on it. So in the overall result of reducing CPU costs and memory usage is that we can pack more application instances into the same amount of hardware. We increase density. We also measured JITServer scalability, so basically how many application instances can a single JITServer instance support. And we can see that with caching, it scales significantly better than without. And the last set of experiments, we measured the effect of network latency. Latency, not bandwidth, because the communication pattern, which is exchanging small message pairs with JVM runtime information, it's latency bound. So caching allows us to tolerate about twice as high network latency, up to 6 milliseconds in this case, because we reduce the number of messages exchanged between the clients and the server by about half. And we can see that in typical data center latencies of under, let's say, 1 millisecond, the performance is very good. So just to bring this, to the serverless aspect of this workshop, one of the main targets, one of the main applications of this is serverless computing. Because in serverless computing, you have short-running instances, and you're charged by the amount of resources you use. So it's perfect target. And one of the main prerequisites in integrating this into a serverless framework, like OpenWhisk, let's say, is automatic sizing and scaling of JITServer resources. And efficient scaling requires, again, scaling out JITServer deployment by starting more instances on demand. And these instances have to be relatively small, so that you provision at a small enough granularity not to waste resources. And you don't want to start these new instances with a cold cache. So we need to share the cache across the instances. And we do it by taking periodic snapshots of the cache. And that's what we share. And persistence also allows us scaling deployment down to 0, which is also important for serverless workloads without losing the cache. There's also optimizations to caching itself, like prefetching, compiled methods. And another direction is caching and reusing profiling data. So for those up to 30% of methods that are not cached and reused, instead we can optimize the indirect overhead of the JIT compiler, which is collecting profiling data. And we still compile from scratch, but we do it earlier, knowing that there is already profiling data for those methods. To summarize, JIT compilation overheads make managed runtime such as the JVM inefficient in the cloud, and the promising approach that we explore in our work is remote or disaggregated JIT, which reduces memory usage but can increase overall CPU usage. And we solve that problem by reusing compiled code across multiple JVMs. The core of this mechanism is serializing dynamically compiled code. So this is implemented in open source in the Eclipse OpenG9 JVM and the JITServer product, so you can try it out. And it significantly improves performance, reduces CPU and memory usage, start and warm-up times, and increases application density in the cloud. Thank you for listening. I'll take questions.
Alexey for the presentation. So any questions? Okay, thanks for the great presentations. So I have one question. So is this like fetching from JITServer happens mostly just at startup time, or it will happens all the way along the program execution?
So as long as JIT compilations happen, so if you have something very long running that runs for dozens of minutes, then the vast majority of compilations happen during the start and warm up, but then occasionally some method will reach the invocation threshold just very late in the execution that is not actually hot. And there are still JIT compilations triggered and we still serve them, but it's mostly for the startup. So this is a startup and warm up phase optimization mostly.
Mm-hmm. Okay, then will you possible to just ship the Java program with the pre-compiled JIT code instead of like running a JIT server. I see in the last discussion, the most some bottleneck comes just from like JIT server in serverless environment.
Yes, so yes, you can pre-populate the local cache and you can put it in your container image, but that requires these separate training runs that complicate your build pipelines, that can increase the resource cost of your CI/CD by an order of magnitude easily, because incremental build of a Java code base that takes 10 seconds, and to populate the cache, you still need to run it until it warms up, and that can take minutes. So instead of that, we do it completely transparently. So I guess that's basically one of the main advantages over a local cache.
Thanks.